Okay, so let's have a class, and we're gonna ask you guys to do the second homework, the exam 2, which is makes exam questions for yourself. We're gonna do the pairs, and when all of you guys are here, we're gonna have to talk about that. Okay, so hopefully Thursday everybody's here, then we'll talk about. We're gonna jump onto a big topic today is lipids. Oxidation. So we briefly review when we talk about at the beginning of the semester. So lipids oxidation. Remember the curve, we talk about sorption isotherm, and the x-axis is water activity or equilibrium moisture relative humidity. The y-axis is equilibrium moisture content. So the curve will be looks like this, sigmoid, and then we said we can cut them into 3 different pieces. So here is 0.25, 0.75, we can just do like that. And we talk about the lipids oxidation that usually is for the food products in the first category, which is monolayer. So the curve is kind of like this. That is lipids oxidation curve. This means the very sensitive to lipids oxidation, usually low moisture food products, corresponding to the water activity is also low water activity foods, which means they're very dry. You can say about that. So this gives us some of the examples. We have a lard, which is swine or pig fatty acids, become sweet. And we also have soybean. Let's say we have a soybean, or maybe have sunflower oil. Those sunflower oil, you put in a glass plastic bottle, loosen the cap, then put at room temperature for about, let's say, 1.5 years. Then they become very oily, very, we call it creamy, and we also call it beamy, and even we say it's a gummy, and showing very huge turbidity. That means the oil, the fatty acids, there has been oxidated. So that's some of the examples. So what is the definition of the lipids oxidation? This means fatty acids in foods or food products spontaneously reacted with oxygen, cause deterioration of food quality. This food quality we also call rancidity. That is a very simple definition. We will talk about is the key thing is fatty acids. The key thing here is the oxygen, and also this process we also call it auto-oxidation. That means spontaneously happen. Okay, so let's just move on to basic general process. What's auto-oxidation will be looks like. So let's give you an example. we talk about this glycerols. We have 3 different locations. That is called stereospecific number 1, stereospecific number 2, and stereospecific number 3. Lots of the times, that could be fatty acids, it's a saturated or unsaturated. So let's say one of them, or unsaturated fatty acids, we will be just, let's say this is the middle guy, okay? We'll just give you example, right? OH. Once this one happens, in the presence of any of the oxidant condition, that could be light, that could be metal, could be oxygen, could be hydrogen peroxide, could be hydroxy bonds, all kinds of things oxidant happen. This will become a free radical and a proton. And this process we call initiation, which means how they start. And this one we call alkene radical, alkyl radical, which means they usually has a unpaired electron. Okay, that's initiation. Then once you have this free radical comes out, they will react it with oxygen. Then they will generate products like this, like this. This is called perioxy radical. Perioxy radical usually it's highly energetic. It will be causing the lipids oxidation usually in another chain of the triglycerols. Typically, if this chain is also have unsaturated fatty acids. So what's going to happen is this guy here, they will react it with, then generate what? A new free radical and H. That's peroxide. Peroxide. And this is a new free radical. And this new free radical could go here. Repeatedly happen. That is, we call it a replicated process. And here, usually this means another chain of triglycerides. So, what are this process cause? This process here we call propagation, same as elongation. Okay, once in the food products, you have these type of the free radical or peroxides. Then what will happen? It could be combined. So, you have free radical and another free radical. They could become a dimer. And you had a free radical, peroxy radical, working with a free radical. that could become a OOO. Or you have multiple these type of the perioxy radical, and they could be working together, then become what? A polymer. So very similar to our polymerization. Then this has become a polymer. Now, this type of reaction happens. That means the oxidation will almost finish. So this is a process we call termination. Now, what type of the products will be created, it really depends on the situation. So the dimer usually happen in the low oxygen level. At ROOR, this happens. Lots of the time is the atmosphere temperature with oxygen. The polymer happens. Usually it's a frying oil at extended heating temperature. So for example, we say it's more than 200 degrees Celsius. That's what will happen, okay? So this is a very general process. What happens for the auto-oxidation, lipids oxidation. Then later on, we will using oleic acids to give you example how we talk about how the detail goes, how that happen. But before that, we want to move on to the next one, is talk about the factors. So what are the factors will affect the lipids oxidation? Now, obviously, the first one is oxygen level. And we know about that. If high amount of the oxygen exposed to be the fatty acids, then the fatty acids easily to be oxidized. But it's not really true. It depends on what type of the oxygen it is. This is going to go back to class 2 when we talk about sublayer electron orbital arrangements, okay? So usually we have oxygen. We talk about O16. What's a sublayer orbital looks like? So we go back to C. This is go back to here. This is 1s, 2s, and 2p. Since it is 8, so what are going to be? Up, down, up, down, up, 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 and then go down. That's very normal. These type of the oxygen we call triplet. Does a triplet oxygen will cause lipids oxidation? Yes, it will be, but not very, how we say it, not very strong. The reason is, if it's really strong, this guy could directly react it with here. They don't need to go through these. Okay, if it's really strong, the triplets, they could directly react it with here. I don't need to go this circle. So what happened is, ideally, from the chemical standpoint, it is triplet oxygen. However, in the food products, we more or less going to expose to light sometimes or metal, especially for the light. There are lots of, we call it a photosynthesizer in the food products. So for example, in a meat products, we have myoglobin. in fresh produce, we have chlorophyll. These generate the color for those products, but it's a photosensitizer, which means they are very sensitive to the light. Once they are sensitive to the light, what will happen? The electron arrangement in the suborbital, especially at the 2p, is not follow Pauli exclusion policy and Hans rules. So what it looks like? That will look like very interesting. The two different situations will happen. So 1s, 2s, and 2p, we don't worry about 1s, 2s. These exactly the same. The difference is here. Based on the Pauli exclusion policy, this should be spin the same direction and in the different sublayer orbital. But what happened here, they could become this. And we mark them 1. There is another situation will happen. 1s, 2s are the same. Okay, not a problem. So that's 1s, that's 2s, that's 2p, these are the same. Another situation where we have, these are in the different sublayer orbital and spin same direction. What will happen is like this. This will happen. And this gives them a name, it's a different letter name, is delta 1. So what happened in the real life, in the food products, the oxygen is not triplet. This is called singlet. Singlet oxygen is very easy to have or trigger autooxidation. The reason is the electron in sublayer orbital did not follow Hans rules and the Pauli exclusion policy, which means they are not in their ground status. They are energized. And they are not only energized, they also can matching the electron arrangements of double bonds in unsaturated fatty acids. So that's why it is very easy to happen lipids oxidation. And these type of situations, we give them a terminology called electrophilic. Okay, so that's the first thing, is the oxygen level and oxygen type, you can say. So that's the first factors. Second factor. Now, obviously, we talk about the fatty acids. Then we talk about the saturated, unsaturated fatty acids. So the important thing is the ratio in the food product, the ratio of unsaturated fatty acids with saturated fatty acids. So we can go back to review what we talked about. We talked already, C18-0, that is stearic acids. We talk about C18,1, that's oleic acid. We talk about C18-2, that is linoleic acid. And we also talk about C18-3, linolenic acid. 3 double bonds, highly unsaturated. So let's assuming the ratio of autooxidation happening For stearic acid, it's 1. Now, even it is a saturated fatty acid, it still will happen autooxidation. Let's say stearic acid is 1. If you have oleic acids, instead of have stearic acids, it will be 100 times faster or more possibility to have lipids oxidation. How about if you have linoleic acids? They will become 1200. How about linolenic acids? There will be 2500. Easily to happen, the lipids oxidation. That's easily understood because we have more double bonds. So that's the first thing. The second thing, that's the second thing. The third one. We already mentioned about the amount of double bonds and also the location of the double bonds. So we're gonna talk about some examples. Okay, this we'll talk about is energy required to happen autooxidation. So let's give an example. I have a very long chain saturated fatty acids, CH2, CH2. What's the energy required to happen autooxidation? This is roughly 95 to 100 kJ per mole. If in a second situation, I have a double bonds, and I have a CH2 close to that. These specific C there, carbons there, we call olefinic carbon. This will be more easy to happen autooxidation from energy standpoint compared to the saturated fatty acids. This will decrease to only 90 kJ per mole. Now, if you have a third situation, I have a double bonds interrupted with a methyl group, so I have another double bonds. What is this type of structure called? This is called the pentadiene. If you have a pentadiene structure, the energy will be decreased to somehow 80 to 85 kJ per mole to happen autooxidation. And more important, this very typical structure can be recognized by a special enzyme called lipoxygenase. Look at the name here. That will easily happen oxidation. And which products is high amount of the lipoxygenase? Soybean. Or lots of the bean products. That's a very important information here. Okay, amount and the location of the double bonds. So number 4, we want to talk about the packaging. Since we mentioned about oxygen, of course the packaging is important. So basically we talk about vacuum package. So remember, vacuum pack does not mean there is no oxygen. They more or less has some. In the older time, when we get a publication or we write a manuscript, we need to write the amount of the oxygen will be penetrated into the vacuum packaging bag with different material. These days, we don't pay much attention to those things. Now, lots of the time in the lab, when we package red meat, we are using called the PVC film. That is a typical aerobic packaging. And we also could modify the packaging, modify the atmosphere packaging. And that's make sure you have an appropriate amount of the, or different combination of the nitrogen, carbon dioxide, and oxygen. So that's a packaging is important. Number 5, whether we have a pro-oxidants. If you in the products already have a pro-oxidants, for example, you're already going through the process with lots of the OH, which means hydroxy bonds or hydroxy ions there, the pre-oxidants there, that's easily to have lipids oxidation. Okay. Now we also talk about is so-called storage temperature. Now obviously the higher the temperature, it's easily to have lipids oxidation. These are some of the factors. They are one of the factors we want to talk separately is whether you existing antioxidant. If in the food products they have antioxidant already there, this will slow down the lipids oxidation speed. The reason is that if you have a free radical, and I have a AH, which is an antioxidant there, what will happen? This free radical will go back, and this will release. That could also happen with peroxy radical. If peroxy radical happens, using this, what will happen? Think about that. This will become H, and this will release. But here's the problem. These things are reversible reaction. If you're using too much antioxidants, more and more A dot comes out, the reaction could goes back. Then will be reversibly generate a free radical. So the concentration of antioxidants is very important. A good example will be tocophenol. This is usually required by USDA, FSIS. The concentration is 10 to 50 parts per million. So FSIS, Food Safety Inspection Service, have a long list of the antioxidants which has been approved to use in the food products. What we have is in our lab, we pay much attention to the antimicrobials. So the list at the beginning is antimicrobials. Then 4 pages later, we have a long list is all the antioxidants. But we don't do much research for the antioxidants in the lab because this is belonging to the food chemistry. It's not for the food microbiology. But I do tell you one thing, there's a long list to talk about the antioxidants, okay? So all these are the very general, we talk about lipids oxidation. The next one, we want to give you an example to explain from the chemical standpoint, the chemical reaction standpoint, what the lipids oxidation really talk about. The example what we're using is oleic acids. And we're going to do an oleic acids example is in sunflower oil. So first of all, what's a sunflower oil looks like? Sunflower oil, this goes here, CH2, 16, CH3. In their stereospecific number 1 position, this is stearic acid. That's SN1. SN2, what will happen is, what we're going to talk is oleic acids. So oleic acids, like that, 1, then 6. You go here, then you go CH2, then you go CH2, 6, and you go CH3. That's oleic acids. Because, yeah, 9. Okay. Sure, that should be 5. Should be 5. Because that's 9 position. 9 position has a double bonds. If you go this position, so it should be 10. So that should be 6. Sorry. Yes, I'm correct at the beginning. It should be 6. So that should be 6. And this position goes here, should be 9. So that's 1, 2, yeah, that should be 9. Okay. 9 position. The next one here. This one I'm not going to draw, okay? Linoleic acid. So, what we're going to do? We want to take this out to move down. Then we can explain what the situation will be looks like. Okay. So we draw it briefly. We move this one out from here. CH2, CH, CH, CH2. Just like we had a CH2, CH2 6, and CH3. So we move this type down. Okay, what will happen? First, the situation. In the presence, have an auto-oxidation situation. I usually say, you buy a bottle of sunflower oil, okay, and then you loosen the cap, the oil is there, reacted with light, with oxygen, will happen. So, what's the first thing will happen? First thing will happen is right here. Free radical will be generated. That goes here. So there's CH2, H is gone, goes here. Alkyl radical. Okay, that's initiation. Second step, what will happen? Remember, oxygen gonna be there. So oxygen will go. So what will be looks like? Lots of them are the same. Not a problem. These are exactly the same. Will be there. So perioxy radical. Okay, at this moment, perioxy radical is highly energized. Look at the sunflower oil. Specific number 1, number 2, and number 3. We find at specific number 3, there is another unsaturated fatty acids, linoleic acids. So this perioxy radical generated from oleic acids will go ahead to attracting H goes here. They become what? Perioxide. Perioxide. Okay, at this stage, this kind of things happen. Then we are going to the next step. We call decomposition. Decomposition has three things happen. We're going to have to explain to you one by one. First thing, this whole thing is gone. Which means you have this comes out. What's that? Everybody knows. Hydroxy radical. Hydroxy radical. If it's free available in the food products, that basically can react with anything. Which means anything here that could go ahead to have auto-oxidation. So we can say high can react with everything, with every chemical basically. Highly lipids oxidation energized. Okay, once this one gone, what we have? We have this section. But like I said, this section is, I took it out. I took it out from here. So at this moment, I need to move them back. Okay, so I'm going to draw here. Once this one gone, hydroxy bond's gone, what you have is CH, O right here. Then you go here, you have CH, CH, CH2, CH2, 6, and CH3. But remember, I took it out. So I don't have to draw briefly the whole thing here. So what happens is you have CH2. I'll just write all one here. Okay, that's steric acids. So you go here, CH. So we're going to move here. That becomes CH. Then goes here. Then goes CH2, CH2, 6, CH3. Then the next one here, CH, CHO, and also 3. Once this thing happens, they are different scenario will generate. What are the different scenario will generate? Sorry, I should have one thing here because this is happening here. So we should have CH2, 6, okay? Then here, let me use this pen, so it's easy to understand. CH, you have okay, don't forget this guy. This is important. Okay, once you have these things happen, I draw them back. Okay, that's steric acid. This linoleic acid. Okay, what will happen? There are different situations will happen. First of all, this is a decomposition. Okay, we are talking about this decomposition here. We talk about number 3, but I'm going to draw there. What's the number 3 will generate? We'll cut through here. This is the one we call hemolytic beta scission. Same thing as beta hemolytic on the blood agar for bacteria. We'll cut like this. Okay, once cut like this, what happened? What is this one comes up? That's very similar to what? Aldehyde. And then what will happen? To double bonds. Migration will happen. So, what it looks like, double bonds, CH2, 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 6, CH3. That's a aldehyde. This aldehyde, if you know the organic chemistry, this is 1, this is plus 10, that's called uno decano. That's a Spanish nomenclature system, like we mentioned about. It's from the International Union of Purified Chemistry Association. So that's aldehyde will generate. They also could happen is cut from here. Once they cut from here, what will generate? This area. Glycerol aldehyde. Glycerolaldehyde is a non-volatile compounds, which means you may not smell it, but it's contribute to the rancidity. This aldehyde is volatile compounds. But here is the thing. So, what we generate here is glycerol aldehyde or aldehyde. And we call it 2-uno-decano. Okay. But then what happened? You don't forget about this is the whole system. This whole system, you have a free radical there. So this whole thing is an alkene radical. That could directly react with other chemical, generate two different results. So how we explain to you? We just draw this out. All the thing on the left, or 1. All the thing on the right, or 2. That's whole thing is an alkyl radical. Now what will happen? If I have another free radical happens, what's the situation will generate? R1, C, then what? R2, this goes here. Then, what's that? That's ketone. That's one scenario. Which means, at this moment, this whole chemical is an alkene radical. If you see, if they meet a free radical, somehow in this sunflower oil bottle, they will generate ketone. And let's give you another example. If you have here, okay, this is already highly energized, which is electrophilic. I did not make a free radical. I find another chain, which is also unsaturated fatty acids. Then what will happen? What could happen? That could happen is CHO, then H, then go here. There will be, this guy comes out. Sorry, this is out too. So I rewrite this one, okay? Rewrite this one. Will become O1 CHOH and O2. So what is that? That's alcohol. See, that's alcohol. So, what products will be finally in this bottle? There will be aldehyde. There will be ketone. There will be alcohol. This is something, an old oil, where you take it out, you make, sometimes you smell that alcohol. Like a creamy wine. That's the reason. So this is a very interesting, the chemistry happened here, to talk about from alkyl radical, perioxy radical, then generate the hydroxy radical in the food products. That could be basically reacted with any